So, the so let's start with the second lecture by Ian Wright. So
Don't worry, that I will remind everybody what it's all about. Okay. Right, all right, so at the end of the first lecture, so we arrived at a sort of a basic fundamental problem in the theory of locally compact abelian groups. And that is, given two locally compact abelian groups, G1 and G2, the problem is to characterize the algebra homomorphisms between the group algebras of these groups. In other words, I want to characterize the homomorphisms psi that map the Banach algebra of integral functions, L1 functions on G1 into the Banach algebra of L1 functions into G2. And by taking the Fourier transform, it's equivalent to characterizing the algebra homomorphisms of the Fourier algebras of the associated dual groups from G1, from the Fourier dual G1 to the Fourier dual of G2. So there's a hat missing there, I see already. Now this is just a stepping stone, although it's a big stepping stone to a much more basic problem in the theory of locally compact abelian groups, and that's the problem of trying to understand to what extent the group algebras determine the underlying group. So it's very simple to see that if you have two locally compact abelian groups that are isomorphic, then necessarily their group algebras are necessarily isomorphic. And the question is to reverse this implication. To what extent do these group algebras determine the underlying group? Okay, so it's the so if we could understand what are these algebra homomorphisms, if we could characterize them, then that would give us a good start into understanding this problem, this more basic problem. This is a basic problem that exists in all different categories. We talked about the situation of topological spaces last time. We always associate topological spaces, the homotopy group or homology groups. Trivially, any two topological spaces that are homeomorphic, their homotopy groups are isomorphic. The question is, do we have reverse implications? To what extent do the homotopy groups, homology groups determine that two topological spaces are homeomorphic? Right, okay. So last time we did a bunch of functional analysis, and we saw that, in fact, if there is indeed, if you do have an algebra homomorphism between these Banach algebras, then in fact, on the Fourier transform side, necessarily this algebra homomorphism has to be just composition. So that the Fourier transform of a function, it has to be given by taking the Fourier transform of a function, composing it with a map alpha. This map alpha is going from some subset Y of the underlying dual group of G2 into the dual group of G1. And therefore, we see that this question of characterization becomes just a question of characterizing those subsets Y of the dual group of G2 and those mappings alpha from Y into the dual group of G1, so that for any element in the Fourier algebra of G1 under composition with this mapping alpha on Y gives me an element in the Fourier algebra of G2. Okay. So we came to this problem, you remember, that we started with a very concrete situation of looking at the case where G1 and G2 are both the integers. Therefore, the dual groups are given by the circle group. Okay. So now on the Fourier transform side, we were looking at the mappings from the circle to the circle, so that under composition with that mapping, it preserves the space of absolute convergent Fourier series. That's the Fourier algebra of the circle group. Okay, so we have this wonderful result we discussed. This is the Leibniz-Kahan result from the early to mid 1950s, and it can be phrased to say that the only algebra homomorphisms of L1, so there's just summable sequences into itself, so endomorphisms are the trivial ones. Okay. So we don't have any interesting So what do I mean by that? So for instance, because the dual group is connected, necessarily this set Y has to be the entire, looking at the entire circle group. And then I'm looking at mappings from the circle group into the circle group, and the only mappings that have under composition with an absolute convergent Fourier series gives me an absolute convergent Fourier series. Necessarily, this mapping has to be affine. It just has to take a point on the circle, each of the 2 pi I t, and map it to each of the 2 pi I of some constant plus k times t, where c is some real number and k is an integer. So that was this remarkable result that we discussed, the rigidity result. So absolutely no curvatures. The periodic parts of this mapping, the circle to the circle, is just a constant function, necessarily a constant. As soon as we saw the presence of curvature, we saw that we get knocked out of this space of absolutely convergent Fourier series. Okay, so this is a very nice result. We started with this result. It's a result of hard analysis, and then we reformulated this result as thinking of composition with the mapping of the circle. Okay, that is a algebra homomorphisms from the Fourier algebra of the circle to the Fourier algebra of the circle. These are just the space of absolutely convergent Fourier series. And then we came to this general problem. Okay, now, I decided to completely change this course now, okay? I'm not going to go along this path, okay? I had planned to pursue this. I like this problem. It has a very long history. There's some very interesting cases. For instance, the next case to consider is to swap the roles, to look at the group being the circle group, therefore the dual group is the integers. And the fact that the integers are disconnected, or not a connected set, this has to introduce the necessity of looking at certain subsets of the dual group, not the entire group. We saw some examples, and so it complicated the problem. But eventually this problem goes on, and then there's a beautiful connection with idempotent measures. One has to characterize those, and eventually there is a wonderful solution to this problem. But I'm not going there, okay? Because I was motivated by the fact that in my first lecture, I noticed that half the audience fell asleep, okay? Not your fault at all, okay? My fault, the fact that I just misjudged that the taste of this audience is certainly not about all this algebraic abstract nonsense, okay? So you want hard analysis. We started with hard analysis. The lecture started out well, and then I started to talk about all this functional analysis, okay? So we're not going there. I'm just going to tell you, in fact, I don't even want to write it down. The solution, eventually this is solved by Paul Cohen in the late 1950s. He completely characterized the algebra homomorphisms between these group algebras. And and it's a rigidity result. In some sense, it's only the trivial ones. So we don't have any non-trivial homomorphisms between these group algebras. Again, the answer is those Y's that arise are precisely those subsets that belong to the coset ring of the dual group of G2, whatever that is. I had plans to tell you all about that. I won't. And the mapping alpha from the subset into the dual group of G1 has to be not quite affine. We have to relax that, piecewise affine. There's a very specific definition of what that is. That notion of piecewise affine and the fact that these subsets should be in the coset ring of the dual group. This was all sort of realized by Walter Rudin. He really started us off on the right track, and eventually Cohen solved the problem. Okay, fine, nice, but you can forget about that. Let's go back to hard analysis. Okay, so now I want to actually go to a problem of Gahan. Okay, I put this side by side. Gahan, of course, was involved in the solution, complete solution of the only mappings from the circle to the circle that preserve under composition the space of absolute convergent Fourier series is just the trivial, it's the affine maps. Then he asked, well, what if we relax? What if I take, so now I want to, again, we're going to look at mappings from the circle to the circle. But now we want to relax the condition. Suppose I start with an absolutely convergent Fourier series. Okay. And then I look at the composition with this mapping. So just a change of variables we discussed. Instead of insisting that I end up in the space of absolutely convergent Fourier series, suppose I relax it to the space of uniformly convergent Fourier series. Okay, of course, an absolute convergent Fourier series is a uniformly convergent Fourier series. So let me remind you that this space this is a subspace of continuous functions that when I look at its partial Fourier sums, so I'm summing frequencies from minus n to capital N, I look at the Fourier coefficients of f e to the 2 pi I n x. Okay, and I want to understand when these converge uniformly. Okay, so that's now, this is no longer an algebra, okay, like the space of absolute convergent Fourier series. So we're going to drop this algebraic nonsense, okay, and where this is a Banach space, okay. So in fact, I've given a norm. So if I take an absolute convergent Fourier series, I'm going to look, of course, if F has an absolute convergent Fourier series, then these guys converge uniformly. That means they converge in the L infinity norm. So in particular, this sequence of numbers has to be bounded, so the supremum is finite. Now, a little bit of functional analysis, okay, sorry, tells you that if you have a continuous function where this is finite, then necessarily it has a uniformly convergent Fourier series. So it's a kind of an if and only if here. And this gives me a norm on this space, and it makes this a Banach space, but not a Banach algebra. Fine. Okay, but we can still ask the question. All right, so let me remind you of what the mappings we discussed this last time, what they look like. So when I take a point e to the 2 pi I t, then this gets mapped to e to the 2 pi I of a again a real function psi of t, but I can psi actually comes, as we saw, it has a periodic part. So phi of t plus a linear part, So this is periodic, one periodic. Okay, and this is the linear part. Okay, and this comes with the coefficient, which is an integer. So L here is an integer. So we have that if I start with a absolutely convergent Fourier series, here we go. So this means that the Fourier coefficients are summable. Okay, then I would compose it with this map. F composed by, as before, we get the following sum, trigonometric sum, e to the 2 pi I n times psi of t. Okay. And therefore we see, so let me, so this was a question, so I should have said it. This is, I want to know when does this happen. This is Johan's problem. I don't know if I want to, so let me give this now a name. This is equivalent now. So I'm going to, so the fact is that we have that this guy, I'm going to call this, what I want to know is when is this norm? So when is this a uniformly convergent Fourier series? Okay, for all, this is the question for all functions that have an absolute convergent Fourier series. So I'm going to call this is the Johan problem, call this dagger. I want to characterize those mappings phi of the circle that have this property. Now, again, as before, notice this is completely equivalent. This is completely equivalent just by taking. I'm just trying to test whether this has an absolute convergent Fourier series. So I just want to take this this bond norm on this space and test when it's finite by the triangle inequality, using the fact that I'm starting with an absolutely convergent Fourier series, this actually suffices to actually test whether I look at these pure exponentials, e to the 2 pi I n of psi, compute its norm, uniform norm, on the circle when is this uniformly bounded in little n? Exactly the same question, okay, as before. Okay, so certainly if this is true, then I certainly have that this is true, just by the triangle inequality, and then now again just testing this on simple functions, just cosine and sine at e to the 2 pi I have a certain frequency. I see that this necessarily has to hold. Okay, so let's unravel this. Okay, so what do we have here? So let's look at the left-hand side. So I take the supremum and little n. I'm looking at this pure oscillation, e to the 2 pi I n of psi. I have this uniform norm. This is given in terms of a supremum. Let's look where it is. Here it is on this board. It's a supremum in capital N. So now I have a double sup in little n, sup in capital N. And then I have to take the partial Fourier sums of this pure oscillation. And then I have to compute an L infinity norm, which is also a sup. It's a supremum as a function of the variable on the circle. So I get a sup. So sup in little n, sup in capital N, sup and t on the units mod 1, it's a real number mod 1, it's a point on the circle. And then what do I have here? I have to compute the Fourier partial sum. What is the, I take a function, I compute its Fourier partial, that's just convolution with the Dirichlet kernel. So I'm integrating from -1/2 to 1/2. I'm looking at this pure, I'm convolving e to the 2 pi I n of psi t minus s. So this is a function of t. So I'm taking the L infinity norm as a function of t. I'm convolving this guy with the Dirichlet kernel at s ds. And I've got to show that this is finite. Okay, so let's do one more line. So remember that this dn of s is more, it's sine of ns over n, so it's more of that. E to the I, 2 pi I, n times s over s. So let me plug that in, and so I get another oscillation. Okay, so what we have here is that I'm trying to, now I have a sup, so many sups here. So let me, so I have these two integer sups, and then I have a point mod 1 on the real line. And now I have this principal value integral, so I have to be a little bit careful here. When I write this as 1 over s, I have to now interpret this integral as a principal value integral. I have e to the 2 pi I at n of psi of t minus s. And then I have here plus capital NS. And then I'm integrating against this Hilbert transform singularity. Integrating this against this amplitude 1 over s. And I want to know when this is finite. All right, fine. We're back to hard analysis. Okay. So no more of this soft stuff for us. So we want to understand now, this is an oscillatory integral, but it's of a different nature, the types of oscillatory integrals I talked about last week in bed level, because we need to understand there's all these parameters, in this case, just 3 parameters, little n, t, and capital N. And we have to understand when this is uniformly bounded in these parameters. So I have to understand the cancellation. Now, before we were just only interested in oscillatory integrals given by a pure oscillation, e to the 2 pi I, some real value phase function. And so we understood that by understanding when this oscillates a lot, when is the phase changing quickly, so that the 2 pi I is quickly going around the circle faster and faster. I'm picking up a lot of positive values as negative values, and so I get a lot of cancellation that way. And that was the only thing we were obsessed with. But now we have to marry this cancellation coming from the oscillation with the cancellation coming from 1 over s. Because when you integrate 1 over s over a symmetric interval, you get 0. And so we have to now marry these two things together. So cancellation is coming from two different sources. Okay, so it's a different type of oscillatory integral that we want to look at. Okay, so not an easy problem. So in the case, but certainly Kahan observed there were nonlinear sides, nonlinear. There was not, of course, if I had a constant here, this guy preserves the space of absolutely convergent Fourier series, so everything is great. But he observed that there exists nonlinear, non-trivial periodic functions here where this is true. So that's Kahan. He did a lot of computation together with Katz-Nelson. Okay, so this is the late 1950s. And so they did quite a bit of work saying that, oh my God, it seems like almost every example we tried, it seems to be true. And this led to this remarkable result in 1965 due to Alpart. So Alpart showed that in fact, this thing is finite. So if you go back to call that on the top of that board dagger, dagger holds for all real analytic psi. So for all real analytic mappings phi from the circle to the circle. That's one thing. That's quite. So for any real analytic psi there, it's true. Okay, so, and he also observed, there exist smooth mappings of the circle such that dagger fits. That you can start with an absolute convergent Fourier series, compose it with a smooth mapping, and you no longer have a uniformly convergent. You're outside the class of uniformly convergent Fourier series. Okay. So that was quite a remark. Now, if you go back and look at Alpart's paper, that is an amazing sort of feat that he was really a master learning from Kahan and Katz-Nelson this how to estimate oscillatory integrals in this way. So one of the things I'm going to do is I'm going to give you a very simple proof of this result. That's one of my goals now. And I'm going to need help. I need, again, some guide. And there is a nice connection here. I want to now describe this connection with this problem that's coming from Kahan with a problem from Calderón-Zygmund theory. Okay, so let's describe this. So there is this nice connection with Calderón-Zygmund theory. So Calderón-Zygmund theory, of course, a lot of us here are from the school. It has a very beautiful development, but it got stuck on occasions. In the 1960s, it got stuck. So originally, Calderón-Zygmund were interested in understanding the regularity of certain elliptic PDEs, and that came from that one started to study these singular interval operators that had some homogeneity. The homogeneity was with respect to isotropic dilations, where you dilate all the variables in the same way. That's because the underlying elliptic equation is the Laplacian that treats all the variables the same way. But they wanted to try to, so people, namely Nestor Riviere, who's the main person, but together with the student Eugene Faves, wanted to try to extend Calderón-Zygmund theory to the parabolic setting. Okay, the basic question here is not the Laplacian, but the heat equation. So now I take one derivative in time, and then all the derivatives in space, I take two derivatives. So I'm not treating the variables all in the same way. Okay, so we need to develop Calderón-Zygmund theory. So the singular integrals that come out, and when you're trying to extend this to the parabolic setting, are convolution kernels that are homogeneous, but with respect to parabolic dilations, where I dilate the time variable differently than the space variable. And they wanted, and the original argument of Calderón-Zygmund from their 1952 seminal paper does not work. Okay, and so this was a sticking point, but the application was important. So eventually they resolved this, and we have Calderón-Zygmund theory. It went through, and now we know how to handle singular integrals with respect to any kind of these not anisotropic dilations. And so what was led to? So in elliptic theory, looking at Calderón-Zygmund's original paper, to handle these things, one way to do this is by the method of rotations. And you can consider such a general homogeneous singular integral operator as an average of Hilbert transforms in one direction. So the underlying key singular integral operator that underpins everything in the elliptic PDE is the Hilbert transform in a given direction. And when you do the same thing in the parabolic setting, you arrive at a singular integral that is what's called the singular integral of the Hilbert transform along a curve. So I'm looking at, again, I have to interpret this in the principal value sense. I'm looking at convolving along the graph. Let me call this S just to make the connection here. And then I'm integrating this a Hilbert transform singularity. So psi is some function. So if psi of S is S, if psi of S is S, this is just the Hilbert transform in a fixed direction. Easy to analyze. But what comes up in the very basic parabolic one is if psi of S is S squared. And now we have this Hilbert transform along the parabola. And now it's a mystery. Is this even bounded on L2? Okay, so let's see. So if we ask, and this was of course the question, even just with S squared, that Nestor Riviere asked Eugene Faves for his PhD thesis. That was his PhD problem, was to understand, is this bounded on L2? So it's a multiplier. It's convolution with the distribution. That distribution has a Fourier transform, and that Fourier transform is the following. It is an oscillatory integral. It's taken in the principal value sense. I'm integrating from minus a half to a half e to the 2 pi I eta times psi of S plus c times S. I'm integrating this against S. And I want to know if this is bounded on, if this is a bounded function. Right? This is what it means. So I need to take, let me give myself, I need to look at the supremum over c and eta of this multiplier. So that's taking the supremum over c and eta of this oscillatory integral and asking, when is this thing finite? That's the question. So for just the function psi of S equals S squared, that was Faves' thesis. Okay. Whoa, wait a minute. Let's not go too far. Let's look at this. Let's look at that board up there. Where is it? Oops. Have I hidden it somewhere? Sorry. Sorry. Can anyone see the top of the middle board? Look at this. There is N is C, capital N is, one is eta, one is C. So they're almost the same, except for this problem coming for Kahan is a little bit more involved. It has this extra translation parameter that really puts things, that's an extra monkey wrench into the game to understand. Okay, so they're very similar. And this group, people that started to evolve, think about these types of oscillatory integrals. Once Faves did this with S squared, you did this by using the method of descent for oscillatory integrals. Okay, complicated method. That method doesn't really work for S cubed. It does work, but it's just a whole new argument now you need. And so we really needed to understand this in a much more robust way. And so this took on a whole life. So Nestor Riviere and Eugene Faves then reached out to Alex Nagel, Steve Wanger, Eli Stein, and started getting them involved and tried to understand this problem. And so here, and there was no connection made at that time. So these two problems evolved separately. And what happens sometimes. But now we see this connection. Okay, so now what I'm going to do, so in particular, okay, let's take a break. I need to rub off the boards, okay? And Diogo says, check here, read your newspapers, and check it. So let me just take a moment here. We'll come back to this interesting historical development. And it was much, much later, in fact, that there was a connection that was made between two problems. Now, how do I find, can somebody help me with the top board measure? Could you take the top board now, please? And leave, yeah, leave the under one up there. So just the top, just the top. Right, so we have this very nice, so I will, I've already erased it, unfortunately, Alpar's, oops, okay, so the Alpar result was here, so maybe I will keep this on the, briefly, on the board here. So remember here, this is a little bit. So we're trying, Alpar's result is to get the super uniformity so that I have this extra parameter here and integrating with respect to the Hilbert transform singularity. We want this. Alpar showed this is true for any real analytic function, and he showed that this is actually false for certain smooth. That was Alpar's result. Now we have this result of Nagel. We have this result of Alex Nagel, Eli Stein, Steve Wagner from this work that was done in the 70s. There's a series of papers. You put them all together, you see that there exists that for every real analytic, this is one result, psi, this problem, this multiplier, this oscillatory interval, as a function of these two parameters, is a bounded function. And so it is a bounded function for really any real analytic curve. And they also showed that there exists smooth psi such that n psi is not a bounded function. Okay, so that's very much parallels Alpar's result. Okay, so much Alpar's result is more difficult than if this is real analytic. I have this extra translation parameter that is problematic, that you actually get this boundedness. So they prove an easier result. However, this is harder. It's much easier when you have this extra parameter to show that it's false for some smooth functions. And then this becomes a little bit harder to see it's still false if you remove that extra parameter. So we have these two parallel developments. Okay, so now I would like to talk about an extension and give you so what I would like to prove to you is a very simple how I want to prove Alpar's result. Okay, but let me extend it at the same time. I'm going to actually take I'm going to take the real analytic mapping from the circle to the detours. So I'm going to extend it into higher dimensions in this simple way. Okay, so real analytic. And so I can talk about, so the proposition here that I want to prove for you is that this mapping that takes absolute conversion for a series of many variables, and then I take the composition with this mapping, this gives me a function on the circle, and I show you that it's uniform conversion, has a uniform conversion for a series. So this is a strict extension. Okay. So this is the proposition I want to prove. Okay. So let's just remind ourselves, so what is this mapping, real analytic mapping look like? Well, it's going to be associated, right? So there's going to be now a d-tuple. So I have a d-tuple. Everything is vector value now. I have a d-tuple of real analytic one periodic functions. So these are real analytic one periodic functions. Okay, one variable. And I want, and then this L, there's also going to be a d-tuple of integers. So that's just a lattice point in ZD. So any real analytic mapping from the circle into the detours has this representation. Okay, exactly in the same way. We just do it component wise. So there is a periodic part, and then there is a linear part given by a lattice point. Okay, so let's see what this is equivalent to. So now I'm going to sort of get into it. Now we're going to see what this. Okay. So what is the proposition equivalent to? This is. So the proposition, of course, that before it's completely equivalent to, I need to take the supremum. Now I'm looking at lattice points in that D, and now I'm taking this oscillation, e to the 2 pi I pure oscillation. Now I'm taking the dot product of this lattice point with my D tuple of real analytic functions, and I'm also going to add this to the what did I call this? L bar. This is a lattice point in ZD times T. Sorry, this is I'm looking at this function on the circle, and I have to compute the Fourier coefficient, the partial sums, and so this is I have to work out this uniform convergent norm. So let me do that. So this becomes, I'm going to write it all out. I have a huge soup now. I'm going to write it as a supremum over 2 real parameters. And then I'm going to take a point on the circle. I'm going to take a supremum over all points in the D minus 1 dimensional. So I'm going to take this vector, okay, lattice point, and look at its Euclidean norm. That's going to be lambda. And then what's left is a point on the circle. So I'm splitting this up into 2 parameters. And then I have this principal value of integral. I'm integrating from -1/2. It's just a 1-dimensional integral. What would be easier? What does the oscillation look like? In e to the 2 pi I, I have lambda now. And then I take the dot product of omega with phi. But now I'm translating as a convolution. And I have this Dirichlet kernel, which I'm going to write as a linear oscillation over, and I'm integrating against ds over s. Okay, so I need to show this. What could be easy? Okay, so it looks crazy. I've made the problem even harder, but now I'm going to tell you from this experience with this connection of Calderón-Zygmund theory that has been well studied. I'm going to take all the wonderful things that we've learned from that and give you a very simple proof. Okay, here we go. Not abstract nonsense anymore. Okay, so this is hard analysis. Let's do the proof. Here we go. Getting too excited. Okay, so let's set, first of all, let's set psi of a function of s and so this could be a function of a point on the circle, and then a real number mod 1 and a point on the unit sphere. And I'm just going to take the dot product of this vector with this D tuple of real analytic 1 periodic functions. Okay, so this is actually real analytic. This is important. This is, I want to view this as a real analytic function, but now on the manifold of the circle cross the unit sphere. And I want to use analyticity on this analytic manifold. Okay, so here we, so first of all, I claim I want to see, I need to marry somehow the oscillation here and the oscillation, the cancellation that's coming from the oscillation here and the cancellation that's coming from integrating against 1 over s. Okay, so to measure the oscillation here, I would like to have some derivative to be large. So I'm going to suppose, I claim that we may suppose, without loss of generality, we may suppose, okay, that for every point on this manifold, on this compact analytic manifold, for every point, there exists an integer that depends on this point. At least two. Okay, that's going to be nice for me, because I'd like to get rid of at least one of these. When I differentiate, I like to get rid of this linear oscillation. There exists a such that the derivative with respect to the first variable of this function at this point s naught omega naught is not zero. Okay, every point I can find some derivative, and then I'm going to use compactness to stabilize this derivative. I'll do that in a moment. But so I'm going to show you. Let me call this stuff. I want to show you this reduction. Why I can assume that. Okay. It's not. Okay, what does it mean? That there exists a point. There exists a point, S naught, omega naught, on this compact analytic manifold, such that all the derivatives with respect to S at this point vanish for all k bigger than root 2. That's what, okay, let's suppose that for a moment. Okay. Now let me Taylor expand. So let me now Taylor expand this function. Now I'm fixing omega naught, but let me now think of it as a function of S. And let me Taylor expand at the point S naught. So I get the value at S naught, I get the first derivative of psi at S naught times S minus S naught plus 0. All the derivatives vanish beyond 2. So the Taylor expansion, which exists, this is a real analytic function. And the Taylor expansion, of course, by definition of real analyticity, this is actually true. And this is true for all S near S naught. So this is true for all S near S naught. Okay. Now I use real analyticity. This is real analytic on the right-hand side. This is real analytic. Fixing, I want to think of this as a function of S now. Omega is fixed at omega naught. Real analytic and S, they agree on an open interval, so they must agree globally. So this is in fact, for all this, by analyticity. Okay. This is periodic on the left-hand side. This is periodic only when this is 0. So this implies that in fact this guy, even the first derivative, must be 0. Since the left-hand side is periodic, but the right-hand side is not. And the right-hand side is periodic if this vanishes. And so what we get is that this, at the conclusion, we get that as a function of S, it's constant for all S. What was omega? This dot product. And I'm fixing it at omega naught now. And that's constant. So that means I can write one of the phi j's as a linear combination of the others. So one phi j in this d-tuple of periodic function can be written as a linear combination of the others, of the other phi k's. And now I use an induction argument. I've reduced d to d minus 1. Okay, and I carry out the induction argument. And I have to eventually, if I continue going with this thing, I get down to the linear case and I'm done. Okay, so an induction argument our ND reduces matters to star. Well, I can assume this. So I can assume that we're in this situation. Okay. Right. Okay. Wonderful. So now I use compactness. Of this manifold. Okay. So compactness. That again compactness. Oh, so wait a minute. So sorry. Before I do that, I should set this up. So in other words, that for every, and in particular, so now I have star. So from star, okay, I can find a neighborhood. Okay, so that for every S naught, omega naught, in this compact manifold, okay, there exists an epsilon that will depend upon that point. So S naught, omega naught, positive, such that the derivative, the S derivative at this value K that depends on this. So K here, I'm taking this point here, and we know it's non-zero. So I can actually extend that this is going to be bigger or equal to 1/2 the derivative, the K derivative at this point. I'm going to call that, give it a name soon. At X point. This is what I know to be non-zero. So that's just a number. So I can get this in the ball. In fact, let me give myself a little bit of room. I'm going to take this to be all points in the ball of radius twice epsilon. Twice epsilon at the X. Okay. Every point now I have a derivative. On the derivative is only associated with the point itself. And I get a unit. This is just a number now, and I'm going to just extract. And now I use compactness. Compactness now implies that I can cover this compact manifold by a finite taken from 1 to m of these balls, now of radius epsilon. I'm going to call this, let me reduce it to just epsilon j. So I take half of this, this is true here. And this is going to be at these points fj, omega j. On these balls, in fact, on twice these balls, I have this derivative about, these are now fixed numbers. What are these numbers? What do things depend on? What does this K, these J, they depend on psi. Okay, what is psi? Psi does not depend on any of my psi. Where's psi? Where's psi? Here it is. That's given to me. This is that's the mapping. This doesn't depend on little n, capital N, or any of these things. Okay, so this is right. Now, okay, so now what do we reduce to? So what do we have? So we know that so for each ball, so this is a note here. So I'm going to now call these Kj, don't mind, it'll be K of Fj omega J. These are all integer, they're going to be 2. So that we have, for instance, if I take the S derivative of J, Kj in the S direction of psi of S and omega, I actually get that this is at least 1/2 times this Kj derivative, but evaluated now at the center. The center, this is just some number now. So this is a constant depending just on J, which is positive. And this is true for all S and omega that lie in this ball of radius twice epsilon J. That's what we have. We stabilize. Compactness allows us to stabilize these points. This is always a very basic, fundamental type of argument that we use to stabilize parameters. Right, okay, now. Okay, oops, I should. Where does it stick? Okay. Want to help me? No, I can help myself. My daughter would say, Dad, you can do it, come on. So it suffices now. Let me make this statement. It suffices now to bound for each j now. Now I'm just taking for each j 1, 2, up to n. I'm going to slide, now I'm going to call this interval I. This is going to be an integration. I'm going to look at the principal value. And I want to bound this interval. This is from -1/2 to 1/2. E to the 2 pi I. I have this lambda omega dot phi bar of t minus s plus rho s. I'm integrating the Silver transform singularity. Okay, and I want to bound this uniformly in the parameters lambda rho real and t omega. These are all the parameters for the problem, but on this ball of radius epsilon j centered at some point. Fixed. But that's all I need to do. All right. Okay, let me start. So what I'm going to do, you see here, I have the derivative bound as a function of t minus s, right? All I know from the top board is I have that. It's not really s I'm interested in, I'm interested in t minus s. And so I have this, I need to bound this uniformly in this, but now I'm shifting, I have this extra parameter s. And so I'm going to stay in the bowl of radius 2 epsilon j. If I just truncate, so I'm going to write this as an integral, the principal value of s going up to epsilon j, e to the 2 pi I, blah, 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 that will not repeat. And then I have the part of the integral from epsilon j to 1. So that part is, of course, if I integrate 1 over s from epsilon j up to 1, I get a bound of log of 1 over epsilon j. Uniform. And put it up to value, kill everything. Okay, epsilon j is fine. All right, so now I have a bound on my phase. So let me call my phase now. I'm going to call this tau s. That's a very complicated thing here, but it involves all these parameters. It involves lambda, omega, t, and rho. Okay, so I call that, and now let me tailor. So let me now. What do I know? I know something about the kj derivative of tau s on this ball. Okay, so this is simply equal. So this is, of course, bounded below by 1/2 this number, this C, what did I call it? Cj, this is just at most lambda times Cj. Sorry, so this is both, this is this, so this goes away. It's the derivative bound on omega dot that I have control from below, and I still have this lambda. So this is at most Cj times the absolute value of that. And this is true for all s. Less than or equal to epsilon j. Okay, so this is going to be a good estimate. I'm going to use Van der Korp's lemma that I talked about when I have a large derivative. But I need to marry that with this integrate. I need to integrate by parts from below. So I need some bound from below. So this is good. This is good. This part of the integral. So if I look at where s is actually bigger than 1 over lambda to the 1 over kj, and I have this e to the 2 pi I of tau, lambda, tau, sorry. I would need to call it here. So I'm going to write this as lambda times something else. I included lambda in tau sub j, so there it is. This is just tau s ds over s. Okay, so this is by van der Korpit plus integration by Korpitz. Okay, so van der Korpit says that when I have the k derivative bounded from below by lambda, when I integrate this oscillation, I pick up a gain of 1 over lambda to the 1 over kj. But when I integrate by parts of 1 over s, and I'm integrating where s is bigger, then I pick up a factor of lambda to the k. That's why I cut it off here. So I get this absolute constant, only depending on j, times lambda to the 1 over kj, that's coming from integration by part, and I get the decay from van der Korpit. And so I'll get a uniform out. Okay, so I have to marry this singular amplitude with the oscillation. Now I'm left with the integration from s. Remember, from now I'm going to look at where s is now less than 1 over lambda. Even 1 over kj. That's what I'm looking at here. E to the 2 pi I. And I have this, let me write out this tau of s again. Yes, over s. Okay, so now what I'm going to do is I'm going to Taylor expand this thing around 0. Okay, and I have to match the fact that I'm going to do it in such a way that the error to, so how far can I go? I'm going to go up to Taylor expansion of order kj minus 1. So this is coming very close to the punchline here. Is there any boards here underneath? Oh no, I lost all the boards now. Oops. Okay. Where's that stem? There it is. Okay. All boards have been lost, so maybe I'll just. So we Taylor expand. So let me Taylor expand. Taylor expand. And I have tau of s equals tau of 0. Okay, tau of 0. But the first derivative of tau of 0 times s. And then I'm going to have the higher order. And I'm going to write this out. If you remember what tau is, where is tau? Where is tau? There's tau there, I guess. You got the order. Okay. Oh yeah, here's tau. So now I'm looking at orders of derivative 2 and more. So that linear part goes away. Lambda comes out front. I'm going to look at the sum starting from L equals 2. L equals 2, and what I'm going to go up to is kj minus 1. And then I have plus or minus 1 over L factorial. And then I have this omega dotted with phi. And I'm taking the dot product, and then I take the L derivative of that, okay, at 0. Okay, so that's at t. Okay, so sorry. Because this tau here is given when I take the Taylor expansion of the omega dot product of t minus s at s equals 0, I'm evaluating the derivatives at t times s to the k. Okay, so this is s to the L. And I get an error term. Now the important is, what is the error term? So this is just the Taylor polynomial, which I'll denote of order kj minus 1, but it involves all of these parameters. All of these parameters, but it's a polynomial of degree s, and that's of degree kj minus 1. And I have this error term. And what is the error? That's just the difference. And this error, the important is that this error term is what? It's controlled. Now the important thing is, this is the error term is controlled by lambda. Okay, so this error term is controlled by lambda. Lambda. Okay, but now this is just involving that. This is, remember, this has absolute value 1. This has norm 1. So this is just involving some ckj plus 1 norm of 5 prime. So I look at this d tuple and I compute the ckj norm. It's just the supreme norm of all the derivatives of the order kj of this function. Okay, so this is the let me just write it like that. And times s to the kj. So this dependence is fine. This dependence is fine. There's dependence on lambda. And there's dependence on s. Okay, now I stick this in and I make a comparison. Okay. So here, I take this e to the 2 pi I of tau of s, and I'm integrating here. Remember, I'm integrating up to 1 over lambda to the 1 over kj. And I'm integrating ds over s, and I'm taking the difference with this. Now I want to reduce to the Taylor polynomial of degree kj minus 1. It involves all these parameters, t, omega, lambda at s, and I have ds over s. And I'm integrating, I only want to keep it at the same interval, 1 over lambda, 1 over kj. And let's check this. I want to pass from this interval that I'm left with to this interval. Okay. So when I take the difference, what do I get? Well, I get the difference of the exponentials. That's the difference of tau with its Taylor polynomial. That's just the error term. So I get this lambda. Okay, and I get an allowable constant, just the ckj norm of this 5 prime. And now I can integrate s to the kj minus 1 ds. And I'm integrating s up to 1 over lambda to the 1 over kj. Okay. I integrate. Antiderivative of s to the kj minus s to the kj. I evaluate at the same point, I get 1 over lambda. Gives that 1 over lambda. So I get a constant only dependent on j. Okay, and fine. Uniform bound. Okay. So finally, I realize this, so we are left with. So all I've done here, using fancy terms, I have stabilized by compactness the Newton diagram of my phase function. Okay, that's using some. This is, of course, the Newton diagram is kind of trivial. I'm just replacing the phase by some Taylor approximation. And so I'm left with this oscillatory interval over some integral, 1 over lambda to the 1 over kj. That involves a parameter. I have e to the 2 pi I. I'm left with the Taylor degree kj minus 1. My polynomial. So this one, I'm left with this bound. This thing. So notice what I've done is the phase is now a polynomial, but the degree is fixed. That's what I mean by stabilizing the Newton diagram. Changes, I fix the degree. And although I still have this guy, has all of this dependence, all the coefficients, has all the parameters still involved. So I move these things. The Taylor, the Newton diagram is changing, but the degree can't get any worse than the degree. I can't all of a sudden, by changing these parameters, I can't introduce terms of order degree larger. They cannot all vanish except I have a term that has a degree bigger than kj. And now I have this beautiful result of Steinweinger. 1966, they were answering a question of Nestor Riviere, and they say that if you take a polynomial, any polynomial, real polynomial, I fix the degree, then I can integrate e to the 2 pi I of that polynomial against the Hilbert transform singularity, I integrate it on any symmetric interval. And this is an interval that is bounded by a constant that only depends on the degree, not on the endpoints of the interval of integration, not on the coefficients of the polynomial. So I was going to give you a proof of this, but of course I've run out of time. Okay, but anyway, so this but you see we're done. Because now I have this polynomial fixed degree. Coefficient depending on all my parameters. I mean some truncated interval of integration that depends on my parameter. Steinwenger now gives me the rest. So this is uniformly bounded. So I get that this is bounded independent of this guy, only dependent on the degree, not on the coefficient. The degree only depends on KJ. Okay. So that's the simple argument. Okay, see how easy that was? Trust me, it's a lot easier than Alpar's results. Okay, but there's a lot of lessons here of how we use compactness to stabilize various quantities. Okay. All right, so that finishes the very easy part. So tomorrow, next time, which is tomorrow? No. Thursday. We're going to look at this problem now in higher dimensions. This is a one higher dimension extension, but that's an easy extension. I want to now look at functions of many variables. So I'm going to look at mappings from the K torus to the D torus. And things start to get very interesting. This is where the problem got stuck. Okay, so even just thinking, although they didn't think about this result at that time, but they were more interested in trying to understand what happens when mappings from the two torus into the circle. So you're looking at functions of two variables, and the oscillatory integrals were just couldn't be handled. They were just too difficult. But we have Calderón-Zygmund theory that has been developed not only in higher dimensions. These are just still one-dimensional integrals, but Calderón-Zygmund theory has problems that we need to look at oscillatory integrals in many variables, in higher dimensions, with kernels that are multi-parameters, so double Hilbert transform singularities. And so we're going to get into really nice connections. We're going to bring in connections with this famous result of Charlie Pfefferman, that the Fourier series of there are continuous functions on the two torus whose Fourier series diverges with respect to rectangular sums everywhere. And that's going to be our hint. How he proves that will tell us how to solve this problem. Okay, so wait till Thursday.
Thank you. Richard, comments? Questions?
Maybe it was like these counterexamples of alpha and
Yes.
are they highly non-constructive or you?
No, you construct them explicitly. No, in fact, for instance, yes, and you can even take and sort of. So there was a question, for instance. There's some really simple constructions, okay, but they're kind of you just want to do all kinds of crazy things to your function. But even in the case where I take psi to be convex, okay, so that was interesting because I wanted to. So this is going to be my mapping, of my graph on my side. I want to take a smooth. Of course, I need it to be not real analytic, so it's going to behave like maybe e to the -1 over s near the origin. That tends not to work. Okay, so you can actually prove that for those flat curves, those are still okay. And then you just have to construct that. And then you construct a super flat thing. So you really start with taking a bunch of points, and then you construct line segments, and then you can evaluate more or less what these are just pieces of the oscillatory intervals. You just have pieces of lines, you can more or less understand that. And then you see what sort of slopes you need to take and which points depend out, and then you just smooth those out. So it's very constructive.
So for this more general class of functions for which, I mean, this bigger class than real analytic for which the theorem still holds true, you can repeat this kind of argument or.
Okay, now in the 80s, going back to forget this extra. Okay, now let me go back. Forget this extra. Let's just go back to the simple. This is the one that Nagels, Stein and Wenger were considering. So you could now just, okay, now let me just take psi of S to be smooth and convex. Okay, now I have to, because S is actually positive and negative. So actually, I'm going to have to extend this as either an odd function or an even function. And there are two papers in the 1980s, both of them are in Duke. This tells me if I have a convex odd function, this guy is bounded in lambda and rho, if and only if psi satisfies some property, some simple doubling property it's called. So there's a functional, and you insist that that functional doubles. And then if it's odd, or if I forget what I said, you do the other one, there's another condition, which is slightly different, but it's another functional you look at, and you insist that that functional is doubling. And that's a necessary and sufficient condition for when this multiplier is a bounded multiplier. So a lot of work has been done. Okay, so very careful analysis of these things. But this is the easy problem, you see. I'm not shifty, I don't have this translational thing. So a lot of work is also many papers in the smooth category when you have results, but they're not definitive by any means. Okay, so that people just basically just stopped working. That became too hard. But the interesting question is, okay, forget about all this stuff. Let's stick into the real analytic category, but now let's move up in dimensions. And now I have to talk about what do I mean by uniformly convergent? Do I mean rectangular sums? Do I mean square sums? Do I mean spherical sums? All those questions are interesting. And all of those questions nobody could answer. They were just completely silent. I'm going to start with writing down the oscillatory angles. And they look horrendous. I mean, not horrendous. It depends on what you like about oscillatory angles. There's a complicated phase. And now we have a double Hilbert transform, 1 over S, 1 over T. And we have to analyze. So there's a lot more interesting cancellation. And then the answer turns out it's been solved. That problem has been solved now because we've now made a connection with Calderón-Zygmund theory, and we've taken all of our knowledge about Calderón-Zygmund theory, and we went back and we solved that problem completely. And the answer is very interesting. So it's an if and only if question, but sometimes the answer is just in the real analytic category. Sometimes the answer is yes. Sometimes the answer is no. It's not true for all real analytic mappings. You have this property, even for square sums.
So maybe we can advance, but for instance, you're saying that this research by Pfefferman in the 70s can be revisited with this new approach. So,
No, not revisited, but inspired us to think about. So if you look at its construction of a continuous function, that when you look at its of two variables on the two torus, that has a divergent Fourier series with respect to rectangular convergence. Okay. You look at that construction, I will give you the proof of that. I will prove that for you. And it's in the proof, very simple, but it gives the hint how to think about this problem in higher dimensions. So that'll come on Thursday. Yeah, there is an obstruction because that's obviously a negative result that says that there's just continuous functions that have this divergent Fourier series. And that's connected when you write, because what does it mean, a divergent Fourier series? That means I look at the partial sums. So that's what I want to do. And I want to understand when you have uniform convergence. Different question, you want just pointwise convergence. And he showed you never get, forget about uniformity, just continuous functions, this divergence everywhere. But he showed us where to look. And then you can study that. And then when you study that, you find exactly the answer for these mappings of the torus from K torus to the D torus. Yes.
Yeah, it is trying to work at the position. So then if we take A is away from 0, like A is non-zero number and B is any finite number, then this lemma follows easily, right? Because
are you talking about this here?
yes,
Yes.
if you take A is a non-zero number, then this is obvious, right?
You can take what?
Then you can bound this by a constant.
For what? Sorry.
By like since P is a real valued polynomial, we can
Yes.
simply take the modulus inside,
Yes.
and then it is follows because you
No,
only
you get log of D over A. That's extremely important. You get log. So I put in absolute values.
but
The
it is
absolute value on
different.
the S now. No cancellation anymore.
But it's saying it's also not depend. It doesn't depend on A either. Like this lemma.
Absolutely. That's the whole point.
Ah.
Because you see R. Depends on that. We want this uniform now. That's the whole point. That's right.
Yeah.
So this is a super uniform. It's independent of the coefficient. It's independent of A and B, and only depends on the degree. Okay.
I have to, so can B is infinite, like I'm talking about that, whether
And
it's
B can be infinite.
it can be infinite.
Sure. Now, as long as the degree is at least 2, yeah, degree 1, this converges. So degree is at least 2, very simple exercise.
Mhm.
I can let B go to infinity, and this is the convergent integral.
Okay.
You can show that.
Yeah.
So B can be infinity. And then this applies. Still it's constant, only depends on D, doesn't depend on A, doesn't depend on the coefficients.
Okay.
Yeah, so it's a wonderful sort of,
Yeah.
and it applies to, so this is, but our point of view is that somehow we came to the center by Taylor expanding. We have this, all we've done is we've stabilized the degree. That's fine. That's just something that is a uniform thing. But now we have all the coefficients, it's a mess. All this dependence, okay? And the endpoint depends on something that we're trying to get uniform estimates. So this lemma, by the way, simple lemma to prove. Okay, it's not so hard. Okay, I can even show you very quickly. Okay, it's just by induction on the degree. Okay, change of variables, simple change of variables, just changes A and B. I can assume it's monic.
Yeah.
Okay, now I assume it's monic, and now I split the integration from S less than 1 and S bigger than 1. When S is bigger than 1, because it's monic, I can take the d derivative, I get a uniform bound from below. So boundary purpose lemma says when S is bigger than 1, I have a uniform bound. So now I'm just looking at when S is less than 1, and I have monic. Now I compare e to the 2 pi of this monic polynomial with e to the 2 pi of all the other terms of degree 1 less than the monic term. I take the difference, I get cancellation except for that monic term but I'm integrating it into one of rest. So I get estimable positive power up to 1. That's fine. So I've reduced now to the integral of S less than 1 of e to the 2 pi of a polynomial of degree 1 less. And now induction. So that's the proof. That's not how Stein and Wenger actually proved it, but that's a very quick proof.
They use a different one.
Yeah, sadly, they were looking at the wrong place in Zygmund's book. And they only knew van der Korp's lemma for derivatives of order 2. When you have, and here I use the van der Korp's lemma for the derivative of the degree of the polynomial. I took the d derivative and got a uniform bound from below, because it was monic, okay? They didn't know that. They just happened to be looking at the wrong place in Zygmund's book. Kind of a story I was told by those guys. And now so this is why their argument was much more complicated. But if they knew, they would have had this very simple argument. Yeah, those guys should know where to look in Zygmund's book. I mean, who knows? They would better than those guys.
No questions? So let's take a break of 15 minutes. Break.
You how fast? Right?
But yes, you know, you said that this is relaxing. We can just a bit flexible. And 15 minutes break. So yeah, then 35. Then the turn. Then the